when we were finding maxima and minima over closed and bounded domains, so like for example, when we had something like we were trying to find the absolute extrema of, let's say we have the function f of xy equals x squared plus y squared plus 4x minus 6y on the domain given by points in R2 such that x squared plus y squared is less than or equal to 16. So this is an example of like domain is just a disk of radius 4, right? And so maybe of radius 4, and then our domain is this disk including the boundary. And if we were to maximize and minimize the function over this domain D, then what we had to do is, well, we have to find critical points on the interior, and then we have to find the critical points along the boundary. And finding critical points along the boundary was a pretty tedious task, right? Especially if it was like, if D was a rectangle, say, right? Then when we were parameterizing over the boundary to find critical points, we had to do it 4 different times, one for each line segment here. And then we also had to do the 4 corners, right? And so to parameterize like the boundary that's a circle to find critical points, you know, you'd have to do like, this is parameterized by 4 sine squared t plus, well, this would be parameterized by x of t equals 4 sine t, y of t equals, or excuse me, 4 cosine t, y of t is 4 sine t, right? This would be your parameterization. Then you'd plug it in for the function and then find critical points of the function over this parameterization. What we're really doing here is when we're looking over the boundary, we're taking a function, but then we're constraining possible values, right? We're giving a constraint. We're saying that this function now, when we want critical points over the boundary, is restricted to these curves here, like this subset of our domain that is just curves, right? Whether it be a line segment or a circle or line segments that compose a triangle, whatever it may be, right? And so this idea can be generalized here. So the idea is that instead of parameterizing boundaries and trying to parameterize curves and then plugging into the function, the idea is we can find extrema of a function subject to given constraints, or to a, let's say to a given constraint. Let's just work with one for now. But in general, we could have more than one constraint. And so what are we trying to do in the language of this example, right? In the language of this example, what we're trying to do is we're trying to maximize or minimize this function to the given constraint of the boundary circle. And so in this language of constraints, we would say we want to like maximize or minimize. It's kind of silly grammar there, but so we're trying to maximize or minimize this function f of xy, which is x squared plus y squared plus 4x minus 6y, subject to the constraint that x squared plus y squared equals 16, right? If we know x squared plus y squared equals 16 and we're subject to this constraint, well, that's exactly what finding maximum and minimum values of the function along this boundary tells us. And this entire idea right here, maximizing and minimizing functions subject to constraints is solving for critical points can be found using a method called Lagrange multipliers. So this is the method of Lagrange multipliers. So let's let f and g be continuous functions on some open set, on an open set containing the curve g of x, y equals 0. And so this g, this curve g here is going to be what we consider our constraint. And let's suppose f restricted to this constraint, g of x, y equals 0, has a local extremum at the point x naught, y naught. Then what the method, the main method here is, so I'll write it on the next page, then there exists some lambda, which is a real number, such that the gradient of f at the critical point, x naught, y naught, is equal to the gradient of g at the critical point, x naught, y naught, times some scalar lambda. And this lambda is what we call the Lagrange multiplier. And so what this is saying, what this theorem is saying, is if x naught, y naught is a critical point of f restricted to g, then the gradient of f is equal to lambda times the gradient of g. And so this allows us to set up a system of equations. This gives us a system of equations with solutions being possible extrema. So if we have a function f and we're restricting it to some constraint function, then solving this system for x naught and y naught gives us all possible extrema. And so there's a paradigm we can set up to finding possible extrema. So here's the paradigm. And this is a paradigm for finding extrema via Lagrange multipliers. Okay, the first step is kind of just some prerequisite things. Well, one is to determine what the objective and the constraint functions are. And so maybe first let me introduce some terminology here. We call f the objective function because this is the one that we're looking to maximize or minimize. And we call g the constraint function because this is the function that is imposing the constraint. Right here you can see f, the objective function, has a local extremum. That's what we're trying to find local extremum at. And it's restricted to g. So we say f is the objective function and g is the constraint function. So the first step is to determine objective and constraint functions. Also, maybe you're trying to find max or min or just one, right? You want to determine if looking for max, min, or both even, right? Maybe you want to maximize and minimize this function. The next step is kind of the main computation part. It's to set up the following system of equations. We have the equations that the gradient of f xy is equal to lambda times the gradient of g at xy. We also have the constraint function, which says that g of xy equals 0. So these together give a family of equations that we can then use linear algebra or just algebra in general to solve for x and y values that satisfies this system of equations. And then the third step is to find solutions, x naught, y naught, to the system in part 2, or step 2, how about step 2. And then the last step is to plug all solutions, x naught, y naught, back into f. And then from there, you know, the biggest f value is your max, smallest is your min. Okay, and so this is what we'll do. You know, steps 1 and 4 aren't much work. It's steps 2 and 3 in particular that is really kind of the heart of solving problems with Lagrange multipliers. And so I think the best way to understand Lagrange multipliers and how they'll get us what we want is to do examples. So let's keep this paradigm in mind as we solve an example. So let's find the minimum value of f of xy equals x squared plus 4y squared minus 2x plus 8y, subject to the constraint x plus 2y equals 7. And so here, step 1 is kind of done for us in the problem, right? It's telling us explicitly that we want the minimum value, and it's telling us to find the minimum value of f subject to the constraint x plus 2y equals 7, right? And so we know this is our constraint, and f is our objective function. So that's good, right? And now what was step 2? Step 2 is to set up the following system of equations. We want to set up that the gradient of f is equal to lambda times the gradient of g, and we want to set up that g of xy equals 0, right? Well, this is the constraint. If you'd like, g of xy would be x plus 2y minus 7, right? And then it's x plus 2y minus 7 set equal to 0. And so you get x plus 2y equals 7, right? And so what does this look like, this system of equations? Well, we need to calculate the gradient of f. The gradient of f is the x partial derivative. So I'll just kind of remind us what the gradient is, right? It's the vector composed of partial derivatives. And then we calculate the partial derivative of f with respect to x is 2x minus 2, comma, 8y plus 8. Okay, and then we have the gradient of g is dg dx and dg dy, which we calculate to be 1, 2. Okay, and so now that we have our gradients, we set up that the gradient of f, so 2x minus 2, comma, 8y plus 8, is equal to lambda times the gradient of g, right? And now we have that if two vectors are equal, then each component is equal. So this gives us the following equations. We have 2x minus 2 should be equal to lambda, and then we have 8y plus 8 should be equal to 2 lambda. And then we also have, when we're setting up this system here, we also have that g of xy should be 0. So we also have x plus 2y equals 7, right? And from here, we need to, if you'll notice, we have 3 equations with 3 unknowns, but we only care about 2 of them, right? We need to use lambda to find solutions x and y, but we don't, if we can get away without having to solve for lambda, we don't need to, right? And so here, I have an explicit description of lambda in terms of x. And so I can plug that in down here, which will then give me that the second equation reads 8y plus 8 equals 2 times 2x minus 2. And so 8y plus 8 equals 4x minus 4. But then I have also a way of explicitly describing what x is from our constraint. From our constraint, I can write that x equals 7 minus 2y. And now I can plug in x equals 7 minus 2y for x here. Then I will have a function just in terms of y, and so I can solve for a y value. And certainly, you can solve this any way you'd like. I mean, as long as the algebra is legitimate. If you see a way that's more intuitive to you or faster for you, then that's how you should go about it. This certainly isn't the only way to solve this system of equations. And so here we get 8y plus 8 equals 4 times 7 minus 2y minus 4. Looks like we're going to have 8y plus 8 equals, let's see, 4 times 7 is 28, right? So 28 minus 8y minus 4 is going to give us the equation that 16y equals 28 minus 4 is 24, and then 24 minus 8 is 16. So 16y equals 16, which is y equals 1. And so we found a y value here of y equals 1. Okay, so when y equals 1, well, we can back substitute because we know x equals 7 minus 2y, which tells me that x equals 7 minus 2, so x is 5, right? And we found values for x and y without having to solve explicitly for lambda, which is fine. That's totally fine. So now what we need to do is this point 5, 1 is the only possible critical point for this function with the constraint x plus 2y equals 7. And so the last step is to plug in f of 5, 1 and see that we get 27. And to check that this is the minimum, check other values, right? So I won't go through it, but basically what you can do is pick anything that solves x plus 2y equals 7. Like just pick x and y values that solve x plus 2y equals 7. Like I see x equals 1 and y equals 3 is also a solution to this, right? Because then you'd have 1 plus 6 is 7. And or you could have y equals 4 and x equals -1. That's also a solution. And then you like check a handful of these solutions, plug them back in, and see that every value you get is going to be bigger than 27. And that's just kind of, I mean, that's not proof that it's a minimum, but it's an idea that you can check and verify that this answer does make sense, right? What's proof that it's a minimum is that this is the only critical point, or this is the only possible local extremum for f with this given constraint. And so we can have examples in more variables as well, right? We could have, say, let's look at a 3-variable example. What if we wanted to maximize let's say f of x, y, z is equal to x squared plus y squared plus z squared, subject to the constraint x plus y plus z equals 1, okay? And so what's step 1 from our paradigm, right? Let's remember here. Step 1 was to determine our objective functions and our constraint functions and determine if we're trying to maximize or minimize. Right here, it's pretty clear we're trying to maximize. And we also see that our objective function is f because the constraint is x plus y plus z equals 1. So we have that g, and this time it's x, y, z, is equal to x plus y plus z minus 1, right? Because we think of the constraint function as some function g set equal to 0, right? And so x plus y plus z minus 1 set equal to 0 is the same as x plus y plus z equals 1. And step 2 in our paradigm was to set up the equation, or the system of equations, given by the gradient of f is equal to lambda times the gradient of g, and g of x, y, z equals 0. And so for us, first let's calculate the gradient of f here. The gradient of f is going to be 2x, 2y, 2z, right? Because you take all the partial derivatives of f. And then for the gradient of g, well, we look at g up here and we see we're going to get 1, 1, 1 for our gradient. And let's set up then that the gradient of f is equal to lambda times the gradient of g, right? If we do this, then we're going to get the following system. We have 2x equals lambda, 2y equals lambda, 2z equals lambda, and then we also have g, right? That's the second part of our system here. We also have that x plus y plus z equals 1, right? And again, now we're solving, so step 3 is to solve, right, from our paradigm. The third step was to solve. And I think in this example, after step 2, I just kind of kept going. But like once we got to here, this would be step 3, right? This is where then we started solving. And then this was step 4, was to plug it back in, right? And so now we're at step 3, we need to solve this. And again, you can solve this however you want. I think there's a clever way of solving this. If we have x plus y plus z equals 1, well, we could multiply this equation by 2 to get 2x plus 2y plus 2z equals 2. But we know 2x, 2y, and 2z are all equal to lambda. So this is lambda plus lambda plus lambda equals 2, which gives us that 3 lambda equals 2, which gives us that lambda is equal to 2/3. And so we have 2x is equal to 2/3, which tells me that x is equal to 1/3, right? By taking lambda equals 2/3 and then plugging it back in 3 different times. And so if we do this, you can see each time we're going to get x equals 1/3, y equals 1/3, and z equals 1/3. And so this is our possible extremum at 1/3, 1/3, 1/3. And this was step 3. Now step 4 is to plug in. And so we have f of 1/3, 1/3, 1/3 equals, well, that's 1/3 squared plus 1/3 squared plus 1/3 squared, which is 1/9 plus 1/9 plus 1/9, which is 1/3. And so this is our maximum value of f given the constraint x plus y plus z equals 1. And again, if you'd like to verify that this is indeed a maximum, you can pick other points x, y, and z that solve the constraint, right? So pick other values that satisfy x plus y plus z equals 1, right? You could do like 1, 0, 0, say. So, okay. Now that we've seen an example of Lagrange multipliers in 2 variables and in 3 variables, we can kick it up a notch to problems with 2 constraints. If we have problems with 2 constraints, so we're going to suppose f, or let's say w equals f of x, y, z is subject to constraints g of x, y, z equals 0 and h of x, y, z equals 0. Then if f has a critical point at, let's just say xy, then we have the following for the method of Lagrange multipliers. We have that the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. And so now there are two Lagrange multipliers. Okay, and so this serves to make the algebra a lot more difficult when you introduce a new constraint, because there's much more restriction on your possible solutions. So what our system becomes then in the paradigm our paradigm is identical, right? It's just now we have the following system. The system is gradient of f equals lambda times the gradient of g plus mu times the gradient of h. And then we also have g of x, y, z equals 0 and h of x, y, z equals 0, right? So we get this system now instead. And so again, it serves to make the algebra much more difficult, or it can make the algebra much more difficult. But the method is identical. You still identify the objective function and the constraint functions. You still set up this system by calculating gradients. You still solve the system. You still identify maximums and minimums. So let's do an example for two constraints. Let's find max and min values of f of x, y, z equals x squared plus y squared plus z squared, subject to constraints given by z squared equals x squared plus y squared, and x plus y minus z plus 1 equals 0. And so here we're trying to find the max and the min. And then we know that f is our objective function, and the two constraints are g and h given here that I've underlined in red. So what is the next step? Well, step 2 in our paradigm is to set up the system of equations. So we need the gradient of f, which is, well, if f is x squared plus y squared plus z squared, then the gradient is 2x, 2y, 2z, right? What's the gradient of g? Well, g is given by this function, right? This is to say that g of x, y, z equals x squared plus y squared minus z squared, right? Because you need to subtract this over for it to be equal to 0. And so that means the gradient of g is going to be 2x, 2y, but then negative 2z. And how about the gradient of h? Well, it looks like here's h. It's already set equal to 0, so we don't have to move anything to the other side. We get 1, 1, negative 1. 1, 1, negative 1. Okay? And so we get the following system. Whoops, not step 3 yet. We're not solving the system, right? We're just setting it up. And what do we get? We get 2x. So let's, here, before I write the system, let's remind ourselves what the equation of Lagrange multipliers should be. What we have is that the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. And so setting each component equal, here it looks like we're going to get 2x equals lambda 2x plus 1, 2y equals lambda 2y plus 1. We get 2z is going to be equal to lambda negative 2z minus 1. And then we also have our functions g and h. And those were z squared equals x squared plus y squared, and x plus y minus z plus 1 equals 0. And so now this is where step 3 of the paradigm begins, is where we actually start to solve this. And these should not be 1s. Sorry. They are 1s here, but it's mu times each component, right? So this is lambda 2x plus mu, lambda 2y plus mu. And so this looks like lambda minus 2z, and that's not true. So let's do minus lambda 2z minus mu, right? And so this is the correct system because we can't forget the second Lagrange multiplier. Okay, and again, you can tell here that the algebra gets a little more tricky. You're going to have to use some different techniques to solve for x, y, and z here. So what I'm going to do is start by solving for mu from the z equation. from here, I know that mu should be equal to, well, it looks like it's going to be so if I add mu to the other side and then subtract 2z to the other side, I'm going to get negative lambda 2z minus 2z, right? And now I can plug this into my other expressions for mu. And so I have 2x equals lambda 2x plus, and then negative lambda 2z minus 2z. And then I also have 2y equals lambda 2y plus, and then negative lambda 2z minus 2z, right? And so from here, I can solve both of these equations for lambda. Let's solve, let's start with this first one here. And so I'll copy this one onto the next page. So I have 2x equals lambda 2x minus 2z minus 2 lambda z. I can solve this for lambda. I can have 2x plus 2z equals lambda 2x minus lambda 2z. Well, I can cancel a 2 from everything and get x plus z equals lambda. And then I can also pull out the lambda, right? So x minus z, which gets me that lambda is equal to x plus z over x minus z, right? I can do the same thing identically. Well, look here, this equation that I solved for x, or that I solved involving x and z to get lambda, is identical to the equation for y and z, right? It's just a change. All I would have to do is substitute y for x, and then I could do the identical computations. And so that means identically, I could have that lambda equals y plus z over y minus z. Well, then I can set these equal, right? These are equal because they're both a different expression for lambda. And so I have that y plus z over y minus z is equal to x plus z over x minus z. I can cross multiply here and get x minus z times y plus z is equal to x plus z times y minus z. If I FOIL these out, I get xy plus xz minus yz minus z squared equals xy minus xz plus yz minus z squared. And I have some cancellation here. I have an xy here and an xy here. I have a minus z squared here and a minus z squared here. And now I can add this negative xz plus yz to the other side, and that's going to give me 2xz minus 2yz. So this gives me 2xz minus 2yz equals 0. Right? And let me double check here. I feel like I've made an error. So xy okay, I think we're okay. And so this becomes 2z times x minus y equals 0. which tells me that z times x minus y equals 0. And from here, there are two cases, right? There's one case where z equals 0 or x minus y equals 0. Then if z is 0, let's go back to our constraint, right? If z is 0, then we have one of our constraints is that z squared equals x squared plus y squared. So we have 0 equals x squared plus y squared, which implies that x is 0 and y is 0. However, we also have the constraint that x plus y minus z plus 1 equals 0. But if you notice, if all of these are 0, well, then we have 0 plus 0 minus 0 plus 1 equals 0. That's a contradiction, right? We can't have that 0 equals 1. And so that means this case is not possible. So we need to explore the case when y equals x, right? This is the next case that we can consider here, right? And so when y equals x, well, then what do we have? Let's look back to our constraint functions now that y equals x. We have z squared equals x squared plus y squared, which means that z squared equals 2x squared. So z, or well, we can write that z is, sorry, before I do that, let's look at our other constraint function, right? We also have the other constraint function that x plus y minus z plus 1 equals 0. And so this means we have 2x minus z plus 1 equals 0, which gives us that z equals 2x plus 1. Now, this is a much simpler z value than what we would get by squaring that, right? Or taking the square root of that. And so let's plug this z value in. So we have z squared equals 2x squared from the other constraint, right? So this is 2x plus 1 quantity squared equals 2x squared. So we get 4x squared plus 4x plus 1 equals 2x squared. And this gives us 2x squared plus 4x plus 1 equals 0. And now we have to solve this using the quadratic formula. So we have x is equal to -4 plus or minus the square root of 16 minus 4 times 2, so minus 8 all over 2, right? Which is -4 plus or minus, well, 16 minus 8 is 8 over 2, which is -4 plus or minus 2 root 2 over 2, which gives us -2 plus or minus root 2, right? So let's double check here. We have -4, negative b plus or minus the square root of b squared minus 4 times a times c. So 4 times 2 times 1 is 8, right? And then this is all over 2a. So it's 2 times 2, which is 4, which makes this 4, which makes this 4, and which makes this -1 plus or minus root 2 over 2. And so this here we have two solutions now, right? We have that x is equal to -1 plus or minus root 2 over 2. Y is equal to -1 plus or minus root 2 over 2. And then z is equal to, well, we know what z is equal to. It's equal to 2x plus 1. So it's 2 times x, which is -1 plus or minus root 2 over 2, plus 1, which is -2 plus or minus root 2 plus 1, which is -1 plus or minus root 2. So we have two possibilities for the min and the max. And then now it would be to just determine which one is which, right? So we have the points -1 plus or minus √2/2, -1, where let's write them separately. I like that a little better. So how about -1 plus √2/2, -1 plus √2/2, and then -1 plus √2. That's one possibility. The next possibility is -1 minus √2/2, -1 minus √2/2, and -1 minus √2. And what you would do from here to finish up, right? This ends step 3 finally. Step 4 is to plug in. So f of -1 plus √2/2, -1 plus √2/2, -1 plus √2. If you plug this in, you get 6 minus 4√2. And then you plug in the other possibility, which is -1 minus √2/2, -1 minus √2/2, -1 minus √2, and you get 6 plus 4√2. And so you compare values, you see this is the max, and this is the min. And so here's an example of solving critical points of a function with 2 given constraints. And again, you can see adding a second constraint adds a lot of algebra, a lot of difficulty to the algebra. And that's why I wanted to fully go through an example of this type so that you can see the kinds of algebraic techniques that you'll want to use when trying to solve these problems. And this concludes our talk about multivariable differentiation. Our next topic, we will kind of switch gears now and go to double integrals. So we'll be looking at taking the integrals of multivariable functions. And so again, this wraps up our discussions on differentiation in the multivariable setting.